Considering the question, how did the solar system form? And to follow the scientific method, which is what we're really trying to understand now, we're going to start with empiricism. We're going to collect general observations about space and the solar system itself. So here are some observations that scientists have made of the solar system. A few of these will be new for you. Most of them come from the article that you were asked to read on Pluto and the new solar system. If you haven't done that, then please pause the video and download that article and read it. But here are some facts, some empirical facts about the solar system. One is that it's about 3 light years across from one end to the other. If you wanted to send a message from the sun to the farthest reaches of the solar system at the speed of light, it would take about 1.5 years to get there. Another observational fact about the solar system is that it's basically flat. You see in a picture like this and many other pictures of the solar system that as the planets orbit the sun, they're all orbiting in relatively the same plane, sort of like marbles rolling around on a bowl with the sun at the center, or rolling around a dish with the sun at the center. Now, they're not exactly in the same orbit, but certainly they're flat enough to raise questions about whether this is just a coincidence or whether there's some explanation that we need to come up with for that. The composition of the solar system is mostly gas. 99% of the matter in the solar system is in the form of gas. Almost all of that, about 92%, is hydrogen. Almost all of the rest of what there is helium, and there's only the smallest trace of other gases like oxygen and methane and carbon dioxide and ammonia. The other 1% of material is in the form of solids, which includes rocky material that's got a lot of silicon and oxygen in it, metals like iron, mostly iron and nickel, and ices. And ice, I use the word ices rather than ice because if I say ice, you're going to think frozen water, but in fact, lots of other things. Everything else can freeze if it gets cold enough. So for an astronomer, the definition of an ice is any sort of material that is a liquid or a gas at room temperature, but in the coldness of space freezes into a solid. So you can have frozen ammonia, you can have frozen methane, you can have frozen carbon dioxide, you can have frozen water. They all count as ices. The solar system has motion. There are two basic kinds of motion in the solar system, as you probably know. One is rotation. Objects spin on an axis. And then there's revolution, where objects orbit around the sun or perhaps around a planet if they're a moon. The interesting thing about all this motion is that it's not random. In fact, almost almost all the motion in the solar system is in the same direction. It's what we call prograde motion, which is defined as being counterclockwise from above. So if you flew up from the North Pole of the Earth and you look down at the solar system, almost everything is revolving in a counterclockwise direction. Almost everything is rotating in a counterclockwise direction. The only exception to the revolution, the prograde revolution, is some comets, and there are a couple of exceptions to prograde rotation, and we'll mention one of them shortly. The solar system is centered on the nuclear furnace of the sun. Is that a coincidence that the sun is at the very center, or can we explain that fact? And the solar system includes different types of solid bodies. We have the rocky or inner or terrestrial planets that are Mercury, Venus, Earth, and Mars, in that order from the sun out. They are called rocky planets because they're composed mostly of rock, at least their outer layers, what we call their mantles and their thin crusts. But they also have dense iron metallic cores. They're all small compared to the other type of planet. The largest is the Earth with a 13,000 kilometer diameter. Earth in Latin was called Terra, and hence these are terrestrial planets. The smallest is Mercury with a diameter of about 5,000 kilometers. There's Mercury over there. And they also all lie pretty close to the Sun. They're all from Mercury at about 0.4 astronomical units out to Mars at about 1.5 astronomical units. And that's why they're also called inner planets. A couple of interesting facts about two inner planets. One is Mercury. Mercury has a surprisingly high density. As I mentioned, all these inner planets are made mostly of rock with an inner metallic core. The core, being metal, is more dense than the mantle and crust. The overall density of the planet is an average of all of the rock and the iron. Mercury is surprisingly dense, which tells us that it has a lot more iron compared to rock, as do the other rocky planets. And so the iron core of Mercury seems to be quite large in proportion to its rocky mantle or crust. And that's different from the other rocky planets. And again, we'll want an explanation for that. Another interesting fact about one of the inner planets is Venus, which actually is one of those objects that rotates in the opposite direction from everything else. It has what we call a retrograde rotation. It's rotating clockwise as seen from above rather than counterclockwise, and it's a very, very, very slow rotation. You know the Earth takes 24 hours to rotate once. Venus takes 243 Earth days to rotate once, which is actually longer than its orbit around the Sun, which is 229 days. So in fact, a day on Venus is quite a bit longer than a year on Venus. Then we have an asteroid belt. Out beyond Mars, in a large gap, we have a lot of chunks of rocky metallic material, which are the asteroids, and they're smaller than planets. But why are they there? Why is there not a planet in this very, very large gap beyond Mars? Then we have the outer or Jovian planets, named after Jupiter, whose other name in Roman mythology was Jove. They're also called gas giants, Jupiter, Saturn, Uranus, and Neptune. They're called giants because they're all very large compared to the inner planets. From Jupiter at 140,000 kilometers in diameter, that's about 11 times the diameter of the largest of the terrestrial planets, Earth. To the smallest, Neptune, with a diameter of 50,000 kilometers, that's 10 times the diameter of the smallest of the terrestrial planets. And you can see in this picture here, Earth in comparison even to the smallest of the gas giants. They're called gas giants because they're mostly composed of gas. We think they all have a solid core that might be similar to the rocky planets, but most of the planet is atmosphere. Very, very, very thick layer of gases, unlike the Earth. And something else they share in common is that they're all found far from the Sun. From the closest one, Jupiter, which is just a little more than 5 astronomical units from the Sun, 5 times the distance that the Earth is, all the way out to Neptune at 30 astronomical units from the Sun. Another interesting fact is the axial tilt of the planets. Planets don't rotate straight up and down. They all have some kind of axial tilt. You probably know that the Earth is tilted about 23.5 degrees and that tilt is responsible for the seasons on the Earth. What I want to point out here is one of the gas giants, Uranus, has an axial tilt of 98 degrees. That's more than completely on its side. So something seems to have happened to have not only given an axial tilt, bumped all of these planets a little bit, but Uranus actually got knocked over on its side. Finally, we have small icy little objects with rock and ice mixed together, often called dirty snowballs. But these are objects that lie out beyond Neptune, so they're called trans-Neptunian objects, or TNOs. The largest of them is Pluto. You read about them in the article, with a diameter much smaller than our own moon. And then there are other ones. Ceres is not a TNO, it's actually an asteroid. But these are made of ice rather than mostly gas or mostly rock and metal. They are found in basically two locations in the solar system. One is a flat disk that we call the Kuiper belt. It's similar to the asteroid belt, only it's made of chunks of mostly icy material rather than rocky material. And that extends from beyond Neptune at 30 astronomical units out to about 50 astronomical units from the sun, and it's flat. Then there's another sphere, we think, another reservoir of these trans-Neptunian objects, these icy chunks, that actually surrounds the entire solar system in this giant halo. That it goes in all directions rather than being flat, unlike the rest of the solar system. And it extends very, very far out, from 5,000 astronomical units out to about 100,000 astronomical units, which is more than a third of the way to the next nearest star, Alpha Centauri. This is the Oort cloud, and way out in the Oort cloud, these icy chunks are moving very, very slowly in the incredible coldness and darkness of space, just barely being held to the sun by its gravitational pull to mark the outer edges of the solar system.